This is the real-time digital signal processing lab class for spring 2014. Homework 5 solutions, so lots of different things on this particular solution set. We have 3 problems, all from Johnson, Thesaurus, and Klein's book on software receiver design. And I've asked a few modifications to the questions. So we'll go over that today. It'll take up the whole period. It's a pretty big set, homework set. All right, now the first problem sets the stage for a lot of other things we're going to do for the rest of the semester. And it's pretty useful in general. And that is to come up with a very simple way to optimize a mathematical formula, which we've been doing for a while in calculus and many years ago. But this is a useful approach because it's something we can embed in a real-time system. We can also do it on the desktop for simulation. And we do this kind of approach quite often in the receiver. So in the receiver, in a communication system, it can also be used in test and measurement, calibration systems, lots of opportunities to use this. We will come up with a measure of whatever it is that we want to lock onto. So for example, an equalizer design in the receiver, its job is to compensate for the channel distortion. Carrier frequency, and which we deal with a little bit later, carrier frequency, the receiver has to figure out what that is, that the transmitter is using, both the carrier frequency and the phase. So as long as we come up with an objective, some measure of what we'd like to optimize, then we can come up with an adaptive framework that will make progress in updating our equalizer filter coefficients or tracking loop or phase lock loop, whatever it is, to get a better performance in the application. So this measure that we use will be application dependent. We can go after signal to noise ratio, bit rate, closeness to an all-pass response, whatever measure we want to come up with. And then once we have the measure, we can figure out how the subsystem, the equalizer, for example, how those coefficients affect this cost function. And then we can just adapt. So we have, as long as we have a training signal, something we can reference, we can adapt the objective function to either minimize or maximize the measure as appropriate. So this is just the first problem on this. We'll have probably another 5 or 6 problems that use this sort of idea. So we're going to take a objective function and use steepest descent. So in this case, the objective function is pretty well behaved. It's a good starting point. And this objective function that we're going after is what? How would you describe it geometrically as a function of x? I see lots of hands drawing, but the word is quadratic. It's only one word to describe it. How would you describe the shape? Parabola, yeah. Parabola, even symmetry about the minimum point. Okay, and where does that minimum point occur? When x is 4. Okay, so we have a parabola, as best I can draw one. I don't draw parabolas all that often. I have a double root at 4, but there's only one unique minimum value at 4, right? And this objective function is chosen so that the values are non-negative. Right? So once I force the objective, once I find wherever the objective function is 0, I've hit the minimum. So in doing any of these sort of problems that involves optimization, we want to first draw or visualize the objective function, sometimes called an error surface, to see what it looks like. How many minimum are there? In this case, we just have one. It's global. But we might have more complicated objective function shapes, and we have to realize that we may end up in what's called a local minimum or local maximum. It's not the best overall answer, but it may be good enough for our application at hand. All right, so next thing is to figure out how do we do an update on this? And so what we want to do is we're going to start at some value, some initial guess. And now we want to iterate, right? So now we want to make progress toward the optimum answer. Okay. And we like to descend the bowl to hit the minimum point. We're going to do this iteratively, okay? And this is what we do in practice. So an equalizer design, well, again, we'll iterate, we'll adapt to coefficients. This will be homework 7 a little bit later. Given a known training signal, that'll be our reference point. Now here we're just going to be iterating, starting with an initial guess. So if I draw the tangent line, again, as best as, that's a pretty bad tangent line, but so if I let mu here in my update be, if I let the sign here be positive, I'm going to head upwards, right? So if I follow the tangent line, right here it's going to be a very high positive value. If I follow the tangent line, it will just grow without bound. All right, so negative means I want to go the other direction. I want to go backwards, or maybe in this case downhill, not uphill is probably a better way to say it. So I'm going to follow the tangent line. And if I follow the tangent line within the accuracy of my drawing here, which is not, try it again. And I wanted to know where I would hit in the x-axis. It would be there, and that would be my next. If mu was 1, if mu was 1, then what I would do is follow. Actually, I would follow the tangent all the way down. But I don't need to do that. In fact, if I do that, in many cases, I don't get convergence. If I go too fast downhill. All right. And for this case, we're going to see very quickly that we can't guarantee convergence when mu is 1 for all initial guesses. We'll come up a little bit later. So what we do instead is we take a small step downhill, and that's going to be controlled by our step size mu. So we don't want to go the whole way. We'll go some of the way, and we'll control it by mu. And so in practice, a common value of mu for equalizers and lots of other systems, about 0.01, very common, and I've seen as low as 0.001. So we tend to do a very small mu to take small steps downhill in this case. So in the problem, you're asked to look at a bunch of values of mu, and a few things can help you right away. Mu of minus 0.01, what's going to happen there? It's going to go for the maximum, which of course never gets reached. So it's going to just go off, go uphill. What happens when mu is 0? You don't move. There's no update. So that's not very interesting. How about, so then if you look at the other mu values like 0.01, what happens with 0.01? It converges slowly, but eventually it gets arbitrarily close to the point at the minimum, the global minimum. 0.1 gets there faster. We'll see this in plots. What happens at 1? Mu is 1. I heard it oscillates. Yeah. Doesn't converge. And when mu is 10, does something, blows up, something crazy. Okay. So it kind of gives you, just from trying out some numbers, that I know 0 is too small, and I know 1 is too big. So it seems like values between those two would be useful. And I'll do the mathematical analysis a little bit later, but that's just running the code. And so here are the plots. And so what we've plotted here, which describes on the next slide, or next page, I'm sorry. Let me go back. Okay, so this will be what happens over the number of iterations. So we have number of iterations. We have number of iterations here on the horizontal axis, and then what values we get for x for different step sizes. Now here the step size is constant, doesn't change over time. There are more advanced techniques that will adapt the step size. Okay, we will not, in this class we won't discuss those, but just to let you know that there are ways to adapt the step size. And so why might you update the step size? Why might that be helpful? Go ahead.
Because let's say the output is like not changing very much. You might need to
take bigger steps. That's right. That's right. That's right. So the observation is that if you're not making much progress, then you can probably increase the step size. If you're making a lot of progress, iteration, you probably want to reduce the step size, take smaller steps if the tangent's large in absolute value. All right, so if you notice here, all these things, so we have mu of 0.01 and 0.1, and the answers converge to 4. The iterative answers here converge to 4. So again, it's an update formula, so we start with an initial guess, x naught, and we just run this formula over and over again and look at what happens. And so let the number of iterations proceed. Now, when mu is 0, nothing, whatever the initial guess is, we stay with it. When mu is minus 0.1, as you mentioned, we get divergence. When mu is 1, we get oscillation. And you could ask yourself, that's an oscillator. I know what that, I've seen that before. This is a feedback system. Okay, so you can, and I mentioned this in the solution, you can think of this as when mu is 1, you end up with something similar to a pole being on the unit circle. It works out to be very similar in the story. Now here is, I don't tell you what mu is, but mu is, I guess, 10 for this one. For some reason, it didn't show up. But, so it diverges. Okay, so one of the reasons you do these things is you can figure out, okay, how many iterations do I need for this thing to settle down to a value that I like? So when mu is 0.1, I don't need as many iterations. Maybe 10 is enough. When mu is 0.01, I need maybe 100, maybe 200 before it settles down. And so you have to figure out how close do I need to get to the actual answer. And I can just say, okay, I'm going to run this. So either I run this for a fixed number of iterations, or I run it until I get within, or my updates are below some threshold in terms of absolute value. So if I get really, really close to the right answer, like here when I'm at iteration 200, the update from one x value to the next is so small, you might just say, well, anything less than, say, 10 to the minus 5 relative change, I stop. So you can stop for lots of reasons. Third option is just I just run as many iterations as I can until I run out of computational resources. It's another way to do it. So in practice, we're going to have to decide how many iterations to use, and for an equalizer design, for example, it tells us how long the training signal should be. That's as many points as we have to iterate over, and we're done. Okay, so in words, this is now on page 2. This is what we've talked about already in words. First two paragraphs. All right, now this third paragraph, is where I do the mathematical analysis for the range of mu that guarantees convergence. It also is useful in telling us what initial conditions are going to work. Now, in this particular problem, it turns out to be it's pretty nice because the objective function is quadratic, and it doesn't matter where we start. That's unusual. Usually, objective functions are more complicated. And the final answer depends very much on where our initial guess was. All right, now this is something we haven't covered in class, but just give you, this is kind of a neat stuff. And the real details here are in a real analysis class. This is called the contraction mapping, or it's a contraction mapping, also known as the fixed point theorem in real analysis. But it's very useful for us, so let me just give it here. So if I have an update where I update my value of x by passing it through a function and I keep iterating. So this is a very useful result for any iterative algorithm, not just this particular steepest descent approach. I have an initial guess x naught, and I have an interval. This is all real, real valued variables here. X is real and a and b are real. So we have some interval ab that contains all the iterates that we generate through this basically keep substituting back in x to get a new x. There's a fixed point theorem that says that these iterates will converge to a fixed point x star. That is to say, if I put x star back into f, I get back x star. Okay, this is going to happen if the absolute value of the first derivative, so be careful on the text here, this is f prime of x. So if the first derivative is less than 1 in absolute value over the interval that contains all those values that we're going to generate for x, then we will converge to the fixed point. The requirement, necessary condition. So if you look at our particular problem, and you look at applying the update formula, so what we had is we had x of n plus 1 is x of n minus mu, derivative of the objective function, and then we substitute x equals x n. Well, so we have xn minus mu, and the derivative was what? What was the derivative here? 2x. So j of x was 2x minus 8 or plus 8? And then I have to put x of n after I take the derivative. All right, so if I multiply this through, I get 1 minus 2 mu x of n plus 8 mu. Okay. So now this is now my function. So this is equal to f of xn. Right? That's my mapping from the argument of f to its output. So now if I look at, so that's my f of x, I look at the derivative of that, so I have another derivative to take. I end up with 1 minus 2 mu, because the term 8 mu here does not depend on x of n. It's a constant with respect to x. So basically, I end up taking two derivatives now if I go all the way back to the objective function. So the nice thing is if the objective function is quadratic, then my condition for the convergence is a constant with respect to x. It's 1 minus 2 mu. So this f prime of x equal to 1 minus 2 mu does not depend on x. So to guarantee this derivative is less than 1 in absolute value, then we can say that the range of mu has to be between 0 and 1, but not including 0 or 1. And if we do that, we'll always get convergence. And this is independent of the initial guess and the values of the iteration that I get, x naught, x1, x2. Kind of nice. So it's just a nice feature of a squared value. Now, this kind of is nice because we do a lot of least square stuff in signal processing and in engineering. So as long as our objective function is quadratic, we have lots of flexibility in how we do the initial guess, and we'll get convergence. Okay, now I describe here the analogy to pole locations. You should read that. Okay, so then I ask you for I guess analyze the number of iterations and what happens to the objective function as we go. What happens to the value here? And so this is it. So when you pick a particular step size, you have to figure out how many iterations do we need to get to a particular closeness to the right answer. So here for this particular step size of 0.01, which is a very common one, it's going to take, I see a typo here somewhere. Seems to be a typo. All right. So as we plot this, we'll need 500 iterations for a step size of 0.01. If we go back up to the earlier curves on page 1, so again, it depends on how close is close, and certainly, we know when mu is between 0 and 1, not including 0 or 1, we will always make progress toward the minimum value. And so for mu is 0.01, we get pretty close to 200, and of course at 500 we're even much closer than that. So it depends on how close you want to get. But you'll see there isn't much progress between about 220 iterations and 500. So at some point you get diminishing returns, and you decide enough is enough in terms of number of iterations. Okay. So this should have been 0.01. In part C, I asked you to try different initial values, and for different initial values, it doesn't affect the outcome in the sense of getting the final answer, but it takes longer if you're farther away from the optimum answer. So here are different initial guesses from -100 -1,000 to 1,000, and in all cases will converge to the right answer, the minimum value in the objective function. But the farther away we are from the right answer, the longer it will take to converge. But it will converge. And again, the analysis is the same as what we did earlier for the fixed point theorem. I simply repeat it here in the solution set. So I simply repeat the fixed point theorem discussion here. Useful again for determining what initial guesses work. Okay, so more generally speaking, our convergence does depend on the initial guess if the objective function is more complicated than quadratic. If it's quadratic, any initial guess will do, which is pretty cool. That's problem 1. Any questions on problem 1? Okay, in problem 2, it's somewhat interesting situation. We have bandpass pulse amplitude modulation. So in essence, we're going to have a message signal with up conversion. So we have a message, we have up conversion on the transmit side. The channel that's on the transmitter, the channel is ideal. On the receiver, we're going to have demodulation. A low-pass filter as part of the demodulation to extract the baseband component. I have a gain by 2, and then I have my match filter. And from lecture, the match filter impulse response will look like the pulse shape. In this case, the pulse shape was a Hamming pulse. The match filter is just a flipped and slid version. It's a flipped and delayed version and conjugated of the pulse shape. Go ahead. We'll show that in the code coming a little bit later. It's coming. All right. But in principle, this is a bandpass transmission. My message signal is going to come off of 4-PAM encoding. And the original message is, before we get into a bit stream, it's just characters. Each character is 8 bits. It's the old ASCII 8-bit per character sequence or alphabet. And so we'll take each ASCII character of 8 bits, break it into 4 2-bit values, and for every 2-bit value, we will do 4 PAM encoding. So if there is a mistake or an error in any of the 4 symbols that we're going to send, the character won't be the right character. So we have error at the 4 PAM level, but any error at the 4 PAM level will mean the character is incorrect. So even 1 out of 4 mistakes, we send so we have 4 PAM symbols for each ASCII character if 1 is an error. If at least 1 is an error, then the character is wrong. Now the problem is going to come in, and we're going to see in just a minute, there is a value of capital M, which is our oversampling factor, and that's going to be put in here in a way that it is both the oversampling factor as an integer, and it's also a sampling frequency. So it has 2 roles to play for the same value. It's a bit strange. So in this problem, we've got 2 issues. One is aliasing, and the second is the gain of 2. That comes into play. So again, this problem is set up, the transmitter receiver is set up to assume bandpass transmission and bandpass reception. But what we'll find for certain values of M, we end up with baseband transmission and baseband reception, which will throw us off in decoding the bit pattern or the bit stream. Okay, so here's where M comes into play. So M is, again, this is the original code from the book. So M here is the oversampling. This is the number of samples per symbol. So that looks fine and typical. Where it gets a little strange, and then this is just different ways to do the upsampling. So capital N is the number of PAM symbols to transmit. Pulse shape is Hamming window, FIR, even symmetric. Okay, now where M is going to play a second role, which is a little bit strange. Oh, of course, we're going to do pulse shaping. So at the transmitter side, we'll do upsampling followed by pulse shaping. Right? So on the transmitter side, we have bits. Serial to parallel conversion to get 2 bits per symbol. We have a map for a 4 PAM. This gives us an amplitude. And then we have upsampling by M. And we have the FIR filter that's the pulse shaping. So that's a block diagram of the transmitter. Now, where M also plays a role is that now, in order to simulate this, I also have one more role to play. So I also have in here somewhere, we're going to simulate this in continuous time. All I show there is the baseband discrete time processing in the transmitter. I then have to, really, in principle, this is going to go through a D to A, and then we'll do analog continuous time modulation with the cosine. Now we're going to simulate this in MATLAB, so we have to discretize everything. Right? So we have to now sample this continuous time carrier signal, which is the cosine, at fixed frequency FC. And so in this block diagram, we'll bring this down, and now it's all discrete time, so I'm going to be multiplying by a discrete time cosine. And this is where M plays the second role in the system. So we're going to sample, so to get to omega naught, we're going to sample continuous time variable little t And the step size, or the number of samples per second, is capital M. So M is used twice, or used in two different ways, however you want to say it. So I now have a sampling rate that's equal to capital M. And you can see that, so in the solution set, I show, well, if we just take those last 4 lines of MATLAB code, and now I go ahead and sample, I put it in sort of a discrete time framework. So really, N is the length of X, and X is just the output of the filter operation, the FIR, pulse shaping operation. And filter returns as many output samples as input samples. All right. And then what I have is my carrier frequency is at 20 hertz. And then from sampling, what I get is I can rewrite the code here from the book Johnson, Saros, and Klein. And what I really am doing is little t, I'm basically decoupling t as a discrete time index. And then to get the continuous time index, I simply divide by m. Let's say m is my sampling rate. So that tells you now omega naught is right here. So omega naught is 2 pi fc over capital M. Now we know from sampling that we could alias if we're not careful. Okay, so for what values of M do we not alias?
40.
Above 40. Above 40. To be strict.
Greater than.
Greater than 40. We can always fudge the sampling theorem and say greater than or equal to, but for this one, let's go with greater. That's great. At 40, we actually have aliasing. So M equals 40, there's no aliasing. So FC is 20. This means that M is greater than 40, no aliasing, right? So the maximum frequency in this cosine is 20 hertz. Now we also know there's a bandwidth, right, because it's finite observation. And I also know that there's also a bandwidth coming out of the pulse shaping filter. There's some bandwidth in discrete time. So what's the bandwidth coming out of the FIR filter? No, not yet. This is all baseband, right? The first 4 blocks here are baseband. All the frequency content is centered at 0. What's the bandwidth of a Hamming pulse? Or the bandwidth of a rectangular pulse, for that matter? We'll get some answer here.
It would be 1 over M.
1 over M. So the Hamming pulse is of length capital M samples. If it had been a rectangular pulse, then I would know it's 2 pi over M. Averaging filter, all that stuff. All right. So we kind of have an idea. There's some so there's some small bandwidth when M is above 40, right? So there's some small bandwidth that for my baseband signal that I'm then going to go through the up conversion step to center at the carrier. Okay, this is another reason why it can't be 40, because the max frequency isn't just 20. It's 20 plus the bandwidth of what comes out of the baseband processing. So it's a little above 20. Anyway, so M greater than 40 is good. And, you know, I guess we could probably do some analysis. And I think this works, actually. M is greater than 40 is pretty fine. Because this bandwidth is 2 pi over M. It's pretty small when M is above 40. Doesn't affect us much. But we can't use 40. All right, so anyway, so that tells us there's no aliasing. So anything above 40 should work fine. It's all bandpass transmission. There's no aliasing. Everything should be good, and it is. So you run it for 100, works fine. Run it for 1,000, works fine. All right, now when M is less than or equal to 40, it doesn't mean it doesn't work. It just means we have aliasing. And aliasing isn't always a bad thing, because in practice we always have some kind of aliasing somewhere. Okay, so, and we talked about in lecture 4, part 2, this was on sampling and aliasing. The second half of those lecture slides were on bandpass sampling, undersampling to be useful in down conversion. Now that I recorded that because we had a snow day, so it wasn't done live, but it was there before midterm 1. And so this is an example of that. So we have aliasing, whenever m is less than or equal to 40, and we know what the carrier frequency, again, is going to be two pi times the carrier divided by capital M, and the carrier is 20. So I know that if m is 20, my frequency is what? In discrete time, it's going to be 2 pi. So if m is 20, it's going to be exactly 2 pi. And cosine of 2 pi n is what? Always 1. So if m is 20, I now have no upconversion. It's baseband on the transmission side and on the reception side. And now the gain by 2 will throw us off. This also happens when m is 10. What other values of m does this work for? And it gives you multiple 2 pi. So what are all the values of m? So I get baseband, transmission and reception for m equals what? 20. So m in the set 20. What else? 10. 10, 5. Yeah, 5 will also work. What else? Well, it has to be, m has to be less than 40, less than or equal to 40. So would 40 work? 40 does not work. It says 20 works, 10 works. Right, we basically want fc over m to give us an integer. So m is 20, 10, 5, what else? 4, 2, and 1. So they're all the possible values for which we get baseband transmission and reception. And there's nothing wrong with baseband transmission and reception. It's a wonderful thing. But the problem is we set up the receiver to expect bandpass reception. And we have the gain of 2 to accommodate that. So for baseband transmission and reception, that gain of 2 wouldn't be there. There would be a gain of 1 or nothing, identity. Throws off the receiver. Okay, so let's go through some values. For m is 100, no problem. We get back our text message. I wish I were an Oscar Mayer Wiener. So it's from the childhoods of at least the authors, and also for me too. We're in the same age group. All right, so we get the right text message. For m is 20. Nope, we get scrambled text. We get a scrambled receive string back. So there are a few characters that get right. And in fact, we're going to make a mistake quite often in reception. And the reason is that, and we'll see in the analysis, that gain by 2, so whenever we have baseband transmission and reception, the pan amplitudes get doubled. So minus 1 becomes minus 2, minus 3 becomes minus 6, 1 becomes 3, and 3 becomes 6. So I make a mistake on the encoding for minus 1 and 1 on the transmit side. Now, it doesn't mean it's half the symbols, because these symbols are not equally likely. But I have some error rate. I have some error because of this scaling by 2 when I have baseband transmission and reception. Now, here's a case of that. So when m is 18, we don't have baseband, we have bandpass transmission, and it works incredibly well. Remember, in this problem, the channel does not introduce any degradation. There's no additive noise in the channel, and there's no filter model. The channel is identity. Okay, so the only thing we're really looking at here is the effect of aliasing on what's happening. And the aliasing is occurring at the carrier, for the carrier frequency, being used at both the transmitter and the receiver side. So 18 is fine. Now, in a system, in a practical system, we are going to have noise, and so in practice, we'd like to have more oversampling than less. Okay, so that's just a comment here in the solution set. if we had noise, which we don't, but if we had noise, we would like a larger M value. And the more samples per symbol we have, the more samples we have for correlation on the, or match filtering on the receiver side, the more noise or out-of-band noise we can remove or reduce, the better the detection performance, the fewer bit errors, higher the SNR. So that's a good thing. So a higher value of M is a good thing in practice. Okay, but again, the real problem here is, I did a little bit of analysis here on the, in this particular receiver design, we have 2 low-pass filters. And if you think about that, do I really need to have 2 low-pass filters in cascade? It's redundant. I can reduce it to 1 low-pass filter, and I pick the one that has the smaller bandwidth. I can just remove the other one. So what we'll see later on in practice is that low-pass filter that does demodulation, we're just going to use the match filter to serve both roles, the low-pass filter and modulation, demodulation, and the match filter. Why have 2 filters when one will do just fine? All right, anyway, so again, the problem that we've already talked about is the issue here of, for certain values of capital M, we get bandpass transmission when the receiver is expecting bandpass transmission. Okay, now the problem with, I guess I didn't say it here clearly. So the problem with bandpass transmission is the following. So if I, on the transmitter side, I have the message signal times cosine 2 pi fc, and I assume that this is bandpass. On the receiver side, I'm going to modulate by the same cosine. Now I have cosine squared. Okay, so now I have, if I look at this, I have, I'm missing a parentheses. So I multiply by the cosine at the receiver, and so as we know from earlier discussions, I get a version of the baseband signal M of t at baseband, and I get 1 at twice the carrier. And I'm going to apply a low-pass filter to extract the baseband component. Well, the thing is, the baseband component is scaled by 1/2, and that's why we have the scaling by 2 in the receiver, so that the PAM amplitudes are the same at the receiver as at the transmitter. I have to worry about gain once I go to 4 PAM. At 2 PAM, I did not, because I threshold against 0 in the receiver for detection. But for 4 PAM, I have 4 values of amplitude to worry about. D minus D, 3D minus 3D. So the gain has to be right. I have to get the gain right. So again, I scale by 2, expecting if I have bandpass transmission. If I have baseband transmission, I don't have this half. It's 1. Another way to look at it, if this cosine alias down to DC, then I have a half plus a half, I have 1. I don't have to have the gain by 2. The gain by 2 will now throw me off, which is what happens. For M is 20, 10, 5, 4, 2, and 1. Okay. Any questions on this one? Go ahead.
Can we decouple?
Oh, sure. Yeah, this was a strange problem. So the question is, can I decouple the oversampling ratio and the sampling rate? So decoupling is a strong word. In this case, the oversampling factor was the sampling rate. Now, normally what we do, so normally for single carrier communication, the sampling rate is the oversampling factor times the symbol rate. So they are related. But in this case, you know, we forced the sampling rate to be m. It did throw some things off. In other words, you could argue our symbol rate was 1. I mean, there are lots of ways you can argue this. Okay. So they can't be completely decoupled, because there is this relationship between the symbol rate and the sampling rate. So we can't decouple them. Okay. This is a little more complicated, so I have lots of discussion here on this one. The problem that 5.3, this is Johnson, Thoris, and Klein 10.1. The real issue here is that my message signal for PAM at baseband has what average value? 0, right? So if I look at the constellation map for PAM, you know, again, you can pick 4 PAM if you like. My constellation map so assuming the symbol values are equally likely, then the average value is 0 in my baseband message signal. When this baseband message signal of 0 average value then goes through upconversion for bandpass transmission, how much energy is at the carrier frequency? So my message signal has 0 content at 0. This is my baseband message. I then go through upconversion. What happens at DC now goes to the, so when I multiply by a cosine, I shift to the right by the carrier, to the left by the carrier, and I have no energy at the carrier. So good luck finding the carrier when there's no energy at the carrier. This is a problem. Or, well, we do have noise, but we don't have any signal power there. It's a problem. So the good news is if we can do a squaring device or some other nonlinearity that has an even power to it, or its Taylor series has an even power, then I can find energy at twice the carrier if I use a squaring device. The reason for that is that the receiver, if I then go through a squaring device, so what comes in is m of t cosine 2 pi f ct, send us through a squaring device. It's the same trig formula from before. So I get, because of the squaring device now, I get a component at baseband and a component at twice the carrier. But now that component is m squared of t. That average value is no longer 0. There is strength there at DC. Think about, so if I had 2 PAM, what would m squared be? Proportional to? So 2 PAM would be plus d minus d for symbol amplitudes. What's m squared going to be proportional to? M of t is proportional to d. So m of t is either d or minus d. In terms of, yeah, it's d squared. And then we have to multiply by the pulse shape. So m squared of t will be proportional to d squared in the 2 PAM case. So now I have a non-zero average value. In fact, I have a lot of strength at 0. So I'll have lots of strength as a result of going through the squaring device. I'll have this DC component, and I'll have a component at twice the carrier that's quite strong. It's a lot of strength, m squared. Now both noise, if there's noise in the system, noise also gets amplified just as well. All right, so now I can follow this with a bandpass filter centered at 2FC. Now I've got lots of energy at 2FC. I can bandpass filter around 2FC and try to estimate more precisely what twice the carrier really is that I'm receiving. It'll be a little bit off from what the transmitter is using. And the receiver doesn't even know what the transmitter is using. It's trying to find what the transmitter is using. Okay, so go through the simulations on this one. R squared works fine. So R squared works quite well. We get peaks at twice the carrier to lock onto. Comes right out of the signal. If we look at R cubed, what's the average value if we use R cubed? We use still 0, right? So if I do a cubic block instead of a squaring block to the third power, the average value is still 0. So now it's message cubed. On average, that value is 0. So that doesn't help us. We still don't have any energy to lock onto. If M is, if the nonlinearity is fourth order, works great. But now my bandpass filter should be at 4FC instead of 2FC. And any nonlinearity that's got a quadratic component will work. So you found some strange ones. What did you find? E to the R.
I use exponential.
Yeah, E works. Because if you think about the Taylor series expansion of E to the X, it's 1 plus X plus, I forget, something 1/2 X squared, whatever that. It has X squared component in it. So if I then follow it with a bandpass filter at twice the carrier, I pull off the energy at twice the carrier, which is there if the nonlinearity is E to the X. Absolute value works. The Taylor series for absolute value is 1 plus something X squared plus something whatever. There is an X squared term in there. So if I bandpass filter twice the carrier, I have energy to lock onto. We'll use this later. Okay. It's called preemphasis. We'll use it later in lab. All right, thanks a lot. Have a great weekend.